Okay, so what I'd like to do here is I'd like to look at resolving elastic collisions in 2 dimensions in a programming context. So we're going to look at 2 extended bodies, 2 balls in this case, and we're going to see what happens when one hits the other one. What sort of things do you have to do that in a programming context? And what are sort of the equations that you have to work with? I'm not going to actually program that. You're going to have to figure out how to take these equations and put them into the computer, right? That's one of our learning objectives in this class, and we're pretty late in the class, so hopefully you can do that already. If not, you can come talk to me. But in general, I'm going to give you the sorts of things that you need to look at. There's not going to be a lot of physics in this talk, mainly because we've already looked at a lot of these procedures in either the 2D reflections or the 1D collisions. And so we don't really need to go over all of the physics again. You've already seen all of the physics, you've seen all the reasons why. Now we just have to combine them in a satisfactory procedure. We're going to have 5 steps to do that. And it should be fairly simple. What you're going to use this for, the main thing you're going to use this for, is your in-class exercise number 17. And you see the associated exercise there at the bottom. Go ahead and look at that video. That'll tell you what you're going to do. You can also look at it to see a live example of what's going on. It's going to be exactly what you see on the screen here. This collision that I've sort of sketched out is that particular exercise, which is making a pool ball hit a stationary pool ball. That's basically what you're going to do in class with this information. So what you need to start here is you're going to have to start with a inventory of the things that you know. You should always know what you know before you start programming anything, right? You can't really do very much if you don't. So what sort of things have you stored in this ball object that will be useful in the collision? And in fact, there's nothing else stored in the ball object. So let's just look at what those things are. We have a mass. We have a radius. So those are sort of constant properties, objective properties, physical properties, non-changing properties of these balls. Each one could have a different mass. Each one could have a different radius. In fact, they have the same mass and the same radius as far as this pool simulation is concerned. But if you're looking at your final project, looking at your final project, you could be doing something with different masses and different radii. And also, each ball also has a position and a velocity. They have these coordinates that you have to keep track of, and that can change, right? And we're going to look at these as they change for both of these properties. The main point of this is going to be changing the velocity. That's what the collision resolution is. Changing the position, that's going to be something that's handled with your update function, right? And so you'll have to work with that. You should also add some position stuff in your collision resolution algorithm, but I'm really just going to focus on changing the velocities because that's where the main issues are going to be. That's where you're going to get tripped up, all right? So this is the situation in the actual program that you'll be working on in class. You've got one ball. This one's a blue ball. It'll be white in class. And it's got a velocity that's completely horizontal. And then it's going to hit this green ball, which will go off in a diagonal direction after it's hit because they're not directly in line. Also, the blue ball will go up in a horizontal direction as well. So that's what you want to end up simulating in this situation, in this class. So the first thing we want to look at when we do that is we want to look at, actually the collision, right? So, but before we look at the collision, we have to figure out that there's been a collision, right? So the first thing is collision detection. So as the update function goes through, then this ball will keep moving stepwise, so step by step by step, until it actually hits. So what we want to do there is we want to figure out when it hits, right? And that's your collision detection. It's not really difficult for two round objects, right? Two round objects, you've seen that before. It looks something like this. So you see that I've got these two balls here, and you see they interpenetrate. So it's very unlikely that while you're dealing with these floating point numbers, and you're dealing both for position and for velocity, that, you know, at the end of one time step, the two balls are going to be at a position that's directly touching, like I have in the lower diagram. In the upper diagram, you see that you have the two balls interpenetrating. So what you need to do is you need to figure out from that interpenetration whether or not there's been a collision. And now you've done this a lot. You see there, you've done that in the colliding walls algorithm and the 1D bowling algorithm in Unit 2, and in Unit 3, you've done that in the slanted tunnel and in Galton's board. All right, and that's just for collisions. And you've done something similar for reflections, and that's another 4 or 5 programs. So you have a really good idea about what's going on here. Basically, the centers, remember we always keep track of the center of the ball, the centers of these two balls are going to have to be closer than the sum of the radii, otherwise we just allow the update function to execute over and over and over again without calling the collision resolution, because until they interpenetrate, these two balls aren't actually going to collide. After they interpenetrate, we're going to step back and then we'll actually resolve the collision. All right. And when we resolve the collision, we're going to have to figure out the important directions, right? So that's what you did in Galton's board, right? You figured out these directions for two round objects. In some other exercises, you did these things for a wall and a ball, for example, and you figure out the distances between those two things, and you figure out the normals and tangents between those two things. But for this particular exercise, you want to do these two round things like you did last time. And that means we have to define these two directions. One is this normal direction here, and the other is this tangential direction here. And to do that, we just have to look at what the relationship of these two directions are to the centers of these two balls, because we know the positions, right? We know these positions, so we want to use them when we calculate that. And if you go down for the normal direction, I've already done that, right? We have this displacement vector, which is the position of 2 minus the position of 1, divided by the distance, which is the magnitude of that. And that's your normal. And we've done that a couple of times. The normal is a unit vector. It has a magnitude of 1. So if we take the magnitude of this thing, it should be 1. And I hope you can figure that out by yourself by now. And so then you have two components for that. One is the change in the x direction over the total magnitude of the vector versus the change in the y direction over the total magnitude of the vector. So those two components give you the components of the normal direction. And on top of that, you need the tangential components of the vector, right? And those you can get from the normal components. So in some of our simulations, we've used the tangential component as the primary one, and we found the normal component later on. But it's always going to be the normal component where the action happens. It's the normal component where we have the impulse, unless we have some friction, and we're not dealing with that in this particular case. So when you find that tangential direction, remember you just reverse the y component and use that of the normal direction and use that as the x component. And you take the x component of the normal direction and use that as the y component of the tangential direction. That's what's down here. Very, very straightforward after you've done it a few times, and by now you've done it a few times. That's more or less what we've been doing since day 1 in Unit 3. And this is the this is maybe the 6th or the 7th thing in Unit 3. So I think that's all we really have to do in this first part of this sort of video here, is to look at these particular directions. So what we're going to do is we're going to use these to resolve the collision. All right, and we're going to have to get the components of the velocity in the direction of the normal, and we'll reflect those normal components and not do anything to the tangential components, and then add them back up, because that's going to be easier. But I don't think I'll get done with that in the time limit that I'll have for this video, so I'm going to go ahead and stop here, and we'll start with these collision directions. Just assume that you've already seen them in the next video, and we can go on from there when you're ready for that. So go through, review this, look at the things that you've previously done, and then go ahead and look at the next video after that, right? And I'll see you then, or I'll see you in class.